welcome back to Estonia and to the lake house. I spoke to Neil Carson about reading from Iceberg, but that's only half the story. You have to get the data in there in the first place. And today I'm going to investigate write performance of Iceberg. We are being told very often in the cloud community that optimistic concurrency is somehow superior to pessimistic concurrency. I'm going to convince you, I hope, that simply isn't the case. And to do that, we first have to understand what Iceberg actually is and how it writes its data. I want to focus today on the Iceberg REST protocol. There are other ways to write to Iceberg, including going directly at the manifest file, but the Iceberg REST protocol is the one that's implemented by Polaris, and that is also going to be our reference Iceberg writer today. The REST protocol is a simple JSON interface. You send over HTTP a request to update the manifest JSON file, and the server that handles the REST protocol will then go and figure things out for you or tell you to retry if you need to retry. Let's start with a baseline. I'm going to put an Apache Polaris inside a Docker container. As always, I'm going to give it the best possible circumstances by providing it with a RAM drive, similar to my previous tests. And we are just going to write a simple test harness that asks for appends into the catalog. And we're just going to sit here with multiple threads, starting with 1 and going all the way up to 16, and see how fast we can get with the insert performance. Here are the Apache Polaris numbers. You can see we are getting somewhere around 60 commits per second, which means that the latency round trip is between 15 and 20 milliseconds. And that shaded barrier is the margin of where the commits are. They're fluctuating a lot. I'm measuring every second and measuring the commit rate. So you can see it fluctuates from about 50 commits per second to about, give or take, 70, maybe 80. As we expect at thread count 1, there is no concurrency, and their retries are therefore 0. But even at thread count 2, and as we grow up, the retries start going up quite dramatically. In fact, they go up so much that if you look at the 16 thread count test, we actually have a negative scale. We see some very bad fluctuations as we start growing up in the higher thread counts. I want to preempt a critique that I'm sure I'll get from these numbers. This is just running on my laptop. What if we were to put this thing in a cloud? Well, I have put this in a cloud, and here's a setup where I'm using the REST API to Databricks, which does allow you to write to the Iceberg catalog. You can just only read the data back with DocDB as far as I can tell. And the numbers look like this. For reasons that will soon become obvious, I've now had to switch to a logarithmic plot of the commits per second. This is the same Polaris data we have in the orange graph. We can't see the fluctuations as much because of the logarithmic scale. And at the bottom, we have Databricks. And as you can see, the Databricks REST protocol manages to commit somewhere around the rate of maybe 40 commits per minute, compared to the around 60 commits per second that we get out of the Apache Polaris setup. And we have arrived at the lake house. And as always, when we get to our outdoor lab, we're going to start doing some hacking to see if we can prove things. Let's use pessimistic blocking concurrency, the thing we are told is not scalable. And imagine that we have the same scenario that we have in our Polaris test. Multiple clients are coming in via various HTTP requests. And in standard Polaris, if they were racing with another client, they would have to retry. What I'm going to do is I'm going to put a very simple little buffer in place in front of the clients. I'm going to use a high-speed C++ web server to do this. And what we're going to do now is we're going to take the clients that happen to arrive when we can commit to Polaris. And we're going to gather them up. Let's say that 3 of them arrive about the same time when we can commit. We gather them up into a buffer. We construct a new state which is a commit of all three at the same time, 1, 2, and 3. And then we're going to send that commit to Polaris as a single write request. Everyone else who's arriving, we're just going to block them. And we're going to gather them up in a second buffer, doing a sort of sub-double buffering. And when Polaris comes back and says, I've committed the previous batch, give me another round, we're going to commit those. As you can see at 1 thread count, we're actually slightly slower than the Polaris Optimistic protocol. There is an overhead associated with doing this batching, so this is not particularly surprising. But already at 2 threads, we are now running at the same speed as Polaris. And as we start growing up into higher thread counts, we are far outracing Polaris. The pessimistic concurrency is much faster than the optimistic by about 2.5x if you look at the numbers on the plots here. Anyone who's been in the database industry for a very long time will be very familiar with this pattern. This is what's called group commit. And you'll notice that the semantics are preserved. The clients are none the wiser. They just observe that their HTTP request takes a little bit longer. They never have to retry because we guarantee that they will never race because we're handling that in our buffer. The protocol becomes a lot simpler. Can we do better than this? Here's the SQLite implementation. Again, we're using our flipping and flopping web server with pessimistic concurrency. And whoever gets to write inserts data straight into a SQLite table. SQLite has a little bit of storage attached to it. You could use EBS for this. I just used my Docker container for these tests. And that means that when this insert is acknowledged by SQLite, it is safely on disk, and we can therefore acknowledge the buffer back to the web server. We flip and flop back and forth between 2 tables here, and the reason we do that is that that saves us from deleting the data in the table by the batch runner, which we're coming into here. The batch runner is a simple background process. It just sits here, writes to Polaris whenever it can, taking the current buffer and aggregating it into a single write. Here are the SQLite numbers. Now, recall that SQLite is generally not considered a very scalable database. It runs in your washing machine, it runs on your mobile phone, and it runs on my laptop and pretty much everything else. But look at it go. Even at low thread counts, it hits almost 3,000 commits per second compared to the around 60 commit per second we get with Polaris. And as we go into higher thread counts, it keeps on giving, and we hit about 10,000 commits every second. And this is with something that's widely considered one of the most unscalable things you can run. But there you are, outrunning Apache Polaris. With a bit of hacking on the side that I did with an LLM while working on other tasks, we managed to make Apache Polaris and the Iceberg REST protocol go 150 times faster, hitting 10,000 commits per second, using a database that most people consider unscalable and pessimistic locking. For those of you who've been in the database industry for a long time, you might say, wait a minute, 10,000 commits per second is not very impressive. And I would agree with you. That is a pretty low number after all. But that is perhaps a tale for another day. And until you see you all again, I look forward to welcoming you back here in Estonia to the lake house.